y equals -1, x plus 3, x plus 1, x minus 1. Type it in. It's a really nice graph. It's very pretty. It's got lots of max and mins. Nice little hill and valley, you know, options. All right. If I ask you to do the first derivative of this currently how it is, is that easy? No. My suggestion would be to distribute the -1 when you hit end bracket. It screams stop. So we would get -x minus 3. And then put those together, which is x squared plus 1x minus 1x minus 1, because the difference of squares, right? And then distribute. So we get y equals -x cubed plus 1x minus 3x squared plus 3, which you could leave like that, but I would want it in descending powers of x. Now we want to talk about the actual graphs themselves, right? So this one is a what function? Cubic. So if we went to sketch it, the x-intercepts we have pretty easily because it was in factored form to begin with, so -3, -1, and 1. And what can we get from our calculators? Our maximum and minimums. How else could we get from our calculators? Or without our calculators? Pardon? First derivative. So I want everyone to get the max and mins with the first derivative. So we know that that is where the x values are by just finding the second derivative. How we find the y values? Well, we plug them back in. And our coordinates of our minimum is -2.2 and 3.1. And then our maximum is 0.1, 0.2, and 3.1. Something is wrong. This is a negative, I believe. Yeah. Okay. You would have to plug those into the original to get it, correct? Just plug those f's back, or those x's into the original to get the y values for the original graph. Yeah? They're not pretty. I understand that. Okay? So we have -2.2 and -3.1. And then we have 0.2 and 3.1. And then you could get more on the arms if you really want to. We have -415. That's not helpful. So it'll be like something like this. Up, down, something like that, right? Okay, then we were talking about how would we draw the next derivative. Well, the next derivative, if it's a cubic, the next one will be a quadratic because it drops a degree. We agree? So we know that the mins and maxes this becomes a 0 technically, right? So where the horizontal tangents occur is where the mins and maxes occur. So if you want to draw the next derivative, your mins and maxes become the what? X-intercept. So the x value of the min and the max, so 2.2 and 0.2, those become my x-intercepts. Now, what is the graph doing from here to here? It's decreasing. So the graph, the second derivative graph is going to be where? Below the x-axis. That have negative first derivative values, y values. Then what's happening from here to here? It's increasing, so it needs to be above. So it has to be above, and at some point it's going to have to come back down here. But those are still above. People think it's increasing, decreasing. It's not. Those are still above. And then what's it doing from here to here? Decreasing, so it needs to be y values that are below. Now what's going to happen to my next derivative? I just treat it like I did the other one. So to get the second derivative, I now just pretend that this red graph is the original. So its maximum is going to become what? The x-intercept. And then what? This is doing what from here to here? What from here to here? Increasing, so it has to be above. And it's doing what from here to here? So it has to be below. You get a linear equation. So what I always do, and is this the most accurate graph ever? I drew something above and something below. The angle could be totally off, right? The maximum could not be the actual maximum. It could be a minimum or something like that. So they would have to give you way more information if they wanted it to be accurate. Okay, I'm going to give you a graph. This is the graph I'm giving you. Oh, wait. So if you're ever asked to draw the second derivative, do you actually know how to draw it? No, you can draw the first derivative, pretend that is now the original, and draw the first derivative of that, right? Literally. So if you can draw the first derivative of any graph, you can draw the second derivative of any graph, because you can treat the first derivative like the original. So let's look at this one. It's a degree 4-ish graph. So the max is going to drop down. Pretend that's actually straight. And it's going to be my new x-intercept. The min is going to drop up. Not a thing. It's going to go up, anti-gravity, become an x-intercept. And then this is going to go down. We agree? So most people are good with that, and then it goes awry after that. It's because what you have to remember is where the graph is increasing, it has to be above the x-axis. Yes? Okay. So from here to here, what's the graph doing? So my graph of the black graph has to be what? Above the x-axis, correct? I'm thinking it's going to be a cubic, so I'm going to, people are like, but that's not right. It's above. It just needs to be above. People will say, but that's decreasing. I don't care. It's y values that are above the x-axis. Because where f prime of x is greater than 0, the graph is increasing, right? So I need my y values to be positive. Now here to here, what's happening? It's decreasing, which means my y values all have to be below. But they also have to connect back up here, correct? So I just do like one of these. Now could that be way the heck lower or shorter? Yeah. Right? It's not the most accurate graph. We're just doing a very quick sketch. And then from here to here, what is it? Increasing. So my graph needs to be above and needs to come back down to here, correct? So the y values need to be above. And then what's happening from here to here? Decreasing. So below. And that's somewhat of a cubic graph. Make a little sense? Okay. Now we're going to pretend that the cubic function is the original. The cubic function is actually the first derivative. We agree? But now to get the second derivative, we're going to pretend that the cubic is the original. Okay? So I'm going to use... okay. So the minimum of my cubic, I'm going to draw it upwards. It's now going to be my x-intercept, correct? The maximum is now going to be my x-intercept. Do you see how that happens? Those become my x-intercepts, correct? Now, let's look at this part of the black graph. So from here to here, what's happening? That graph is doing what? Decreasing. I know I'm going from a cubic. What's it going to be going to? Quadratic, because I drop a degree each time, correct? So this is decreasing. So I'm either going to have an arrow coming down to it, which means my y values are above, or an arrow coming up to it, which means my y values are below. Because it's decreasing, my y values need to be below the y-axis. People are like, but that's increasing. That doesn't matter. It's the y values. They need to be below. They need to be negative. Then from here to here, it's doing what? Increasing. So I need to have y values that are above, and I need to connect it. Then from here to here, what's it doing? Decreasing, so I need y values below. Can I get the next derivative too? Quadratic turns into a linear. So my maximum, once again, comes down here. My maximum, my blue graph, correct? Then from here to here, what's it doing? Increasing, so it needs to be above. And people are like, how do you know to draw it like that? I could draw it flatter, but it has to be above, and I need to get a line, correct? So, and then here to here, it's decreasing. Get what I'm saying? So the key thing you have to look for is you literally have to look for where the max and mins are, put them as x-intercepts, increasing, decreasing after that, above or below. And literally, if you have the first derivative graph, you get the second. If you have the original, you get the first, then you get the second from using the first as the original, right? It's not crazy. So this one rocks in a way because it says it's continuous, correct? So it means there's no crazy asymptotes showing up or points of discontinuity, removal discontinuities. What is this just? Points, go. You can do those. I believe in you. So we're going to plot our points. We have negative 6, 1, 2, 3, 4, 5, 6, 0. God, I had to reset this thing. This wonderful thing. 1, 2, 3, 4, 5, 6. Negative 6, 0. We have negative 4, 3. We have negative 2, 0. 1, 4. 4, 0. Okay. What the heck does the other information tell me? So, this tells me what? F prime of negative 2 equals 0, F prime of 1 equals 0. What are those? For the first derivative equals 0, what do we find? Max, mins, points of inflection. Now, if I want points of inflection, we talked about this yesterday. This might only give the one special point of inflection, but anytime concavity changes, you get points of inflection. Points of inflection. So you always go to the second derivative to find those. Okay. We're just writing down what we know. What does this mean? Something wrong. What could that something be? It could be a point of discontinuity, could be an asymptote. Problem though is it says it's continuous. I'm a little sketched on that. Okay, when the f prime of x is greater than 0, what does that tell me? The graph is doing what there? Increasing. Increasing, yes. F prime of x is less than 0. Decreasing. Decreasing. F double prime of x is greater than 0. What does that tell me? Concave up. And these are not coordinates. What are these? Domain. And this F prime double prime of x is less than 0. It's concave down. And what is this? F double prime of x equals 0. What do we get when that happens? Inflection point. So it's where your concavity changes, which should make sense. We can discuss that stuff later. Anyways, this one here, basically it says we have a maximum or minimum at -2 and 1. So those are the ones that I really care about. -2 and 1. I'm going to make a blue. Okay? Then it says that this graph is increasing from -infinity to -4 and -2 to 1. Then what is it? Decreasing from -4 to -2 and 1 to infinity. Now, if this were true the way it was sitting right now, what does that give me? Another maximum, correct? So what are they doing to it? They say it doesn't exist at -4. What do they probably have there? Open dot. That's meaner than they'll give you on an AP exam, just so you know. This is a calc assignment I stole from the university. Oh. Oh. Yeah, there's a screw up somewhere in this, because you can't say it doesn't exist and then say it's continuous. So I would say infinite, yeah. It's not differentiable, but it's not saying it's not differentiable. Did it say it's different? I thought it was F prime. Yeah. Connect it. Make it a corner. I read it as F prime, not F. I mean, I read it as F of -4, not F prime of -4. You can make a corner on it, and then it doesn't exist. Corner, cusp, or what else is the third thing? Vertical tangency. You are right. Okay, this is what I wanted you to see for AP. AP does this a lot. They give you F prime and F double prime nicely already broken down for you. Isn't that nice of them? Because what they're doing on their exams is they're not testing, you know, like if I don't give you the derivatives for them, I'm testing whether you can get the derivative of it. And then I'm also testing whether you know intervals of concavity, increase, decrease, whatever, right? If I give you the derivatives, what am I only testing you on? The procedures of, do you know how to find a critical number? Do you know how to get an increase and decreasing? Do you know how to get a local maximum, neither, inflection point? This is what I'm actually testing now. I'm not testing, because sometimes people can't ever get these right, because they can't get the derivative right, correct? So this way, on the AP exam, they'll do this even in the multiple choice. So watch yourselves, because sometimes they'll give you the first derivative and then ask you stuff about it. And you guys go and find another derivative. And I'm like, no, they gave it to you, they were nice. And you're like, oh, well, that's sad. Okay? So I want you guys to find the critical numbers of F. So the critical numbers of points of F, you do F prime. So we would set that equal to 0. And we go, get a thicker marker first. We go 0 equals 16 minus x squared. And then 0 equals x squared plus 16 squared. So this one, we had moved the 16 over, so we get negative 16 equals negative x squared. Divide by negative 1. X squared equals 16. Square root plus or minus x equals plus or minus 4. This one, we'd raise it to a half, or square root of 0. Either way, still 0. This is an addition of squares, which results in no answers, because you're going to subtract it over, and then you're going to take the square root of a negative, and what happens when that happens? No solution. So they want to know where it increases and decreases. So we use our critical numbers on the number line. Negative infinity, positive infinity. I know there's x's in the denominator, so people want to say that there's asymptotes, but when you have an addition of squares in your denominator, there's nothing you can do that will create that denominator to be 0, right? Like if I put any number in here, I need it to technically be negative 16. This x squared needs to be negative 16. Can an x squared ever be negative 16? Negative 16 plus 16 would give me 0. This can never be negative 16, therefore no asymptotes, no restrictions, right? So addition of squares makes you not have a restriction. Okay. So we have negative 4 and we have 4. And we have to run test points on f prime of x. F prime of x equals 16 minus x squared. So try that out. And then the first derivative test is just if it's decreasing to increasing, you have a what? Min. And if it's increasing to decreasing, you have a max. Right? That's your first derivative test. And then find the inflection points. You just need to find the critical numbers of the which derivative? Second derivative. Someone whispered it. So when we plug in a value below negative 4, so say I plug in f prime of negative 5. When I plug negative 5 in here, I'm going to get 16 minus 25, which gives me a negative on the top. The positive will always be bottom. That's what I was going to say. The bottom will always be positive, because no matter what you plug in here and square, you'll be positive, correct? So negative over a positive is a negative. Then say I plug in f prime of 0. I'll get 16 minus 0, which is a positive over a positive, which is a positive. Say I plug in, wow, f prime of 5. I've been sick all week, and you can tell. 16 minus 25 is negative over a positive, which is a negative. So remember, intervals of decrease negative infinity to negative 4, or 4 to infinity. And then intervals of increase negative 4 to 4. Okay. So, using that first derivative rule, the first derivative test, I am going to decrease to increase. So what's happening at negative 4? Minimum. And when we plug f negative 4 in, it just critical, that's why it says critical points. That's why it doesn't say that you have to give the actual value. So minimum is at x equals negative 4. And then this one we increase to decrease. So you have a maximum is at x equals 4. That's why it's not actually asking for the points, asking for the critical values. Yeah. Sorry? The first derivative test literally is just decrease to increase gets you a min. Increase to decrease gets you a min. Yeah, if it was like explain why, then it'd be different, but it doesn't say explain. Yeah. Find the inflection points. F double prime of x. I don't have my paper in front of me. What is it? Help me. What is it? Okay. So then we have 2x equals, we have to set that equals 0. Don't do that on the test. Actually write it equal to 0. So 2x equals 0, x equals 0, x squared minus 48 equals 0, x squared equals 48, x equals plus or minus root 48. 48 breaks down into what and what? 16 and 3, so it becomes 4 root 3. And no solution for the bottom, because it's an addition of squares. Yeah. Good talk.